Hello, my name is Muhammad Iqazah Hamid Khairil, and this is my partner.
Hello, my name is Abdul Fattah Iskandar bin Abdul Malik, matric number 01 BME25F3018.
So today, we want to present about mechanical vibration, a vibration of analysis of an aircraft landing gear. First of all, I want to thank our lecturer, Dr. Nur Rehana binti Shukri, for guiding us through this semester and guiding us through this mechanical vibration. Now let's go to engineering application, which is the action. Point 2, landing gear diagram. Why did we choose an aircraft landing gear? Because it does three vital things. First, it protects the plane structure from cracking during touchdown. Second, it ensures a smooth, comfortable ride for the passenger in the cabin. Third, it keeps sensitive cockpit electronics safe from the heavy vibration shocks. Now let's move on to vibration classification, which is internal component of the landing gear system beside a classification list. We classify our system parameter into standard engineering categories, which is the excitation types consists of both free vibration from the touchdown heat and forced vibration from bumpy runway surface. The bumping is viscous due to hydraulic oil resistant inside the struts. The model uses a linear deterministic response for predictable taxiing behavior, and we represent this as 2 degree of freedom system, tracking the movement of the fuselage mass and the wheel assembly mass separately. Now we go to model parameter summary. This table consolidates the exact baseline parameter used throughout our calculation. We define the fuselage mass at 5,000 kg and the wheel mass of 500 kg, a strut stiffness of 800,000 Newton meter, and tire stiffness of 2,500,000 Newton meter, and damping coefficient of 2,500 Newton second per meter. This value from our system mass, damping and stiffness matrices. Now let's move on to damping characteristic. Using our baseline value, we calculate the system approximate natural frequency to be 12.65 radian per second. This yield a critical damping coefficient of 126,500 Newton second per meter. Dividing our actual damping by the critical value gives a final damping ratio of 0.198. Because this ratio is strictly between 0 and 1, the system is underdamped. This design allows the landing gear to rapidly absorb energy while letting secondary oscillation decay within a few cycles. Next, we look at the mathematical model of our landing gear. We use 3 standard metrics to represent the system. First, the mass metric M. This shows the weight of our 2 separate parts, the heavy fuselage body at 5,000 kg and the lighter wheel assembly at 500 kg. Next, the damping metric C. This represents the hydraulic fluid resistance inside our shock strut, which is 25,000 Newton second per meter. Next is the stiffness metric K. This combines the stiffness of the shock strut and the rubber tire to show the total elasticity of the system. The most important takeaway here is the negative number of the corner of the matrix. Mathematically, these numbers couple the system together. They explain exactly how impact force pass from the rough runway through the wheels and up to the aircraft structure.
So now we move on to spring arrangement analysis. Physically, our elastic elements operate in a series configuration. These components are the main shock strut fluid compliance is Ks and the structural rubber tire elasticity KT. By Calculating their combined equivalent stiffness, we find a total value of 606,060 Newton per meter. This arrangement is optimal because the softer tire acts as the first line of defense for small, sharp runway wrinkles, while the stiffer short strut handles heavy landing deflections. Now we move on to mass influence on response. The sprung mass represents our heavy fuselage at 5,000 kg. Its large inertia results in a low primary natural frequency, keeping cabin acceleration smooth and safe. Next, the unsprung mass is the wheel assembly at 500 kg. Being much lighter allows it to react fast to rapid runway bumps. We also factor in a wheel rotational inertia of 40 kg, which directly dictates braking stability during high-speed touchdown spin-out. Now we move on to eigenvalue interpretation. Our primary mode corresponds to the fuselage bounce. This is the lower frequency where the heavy airframe moves slowly, making it easy to damp out for comfort. Our secondary mode corresponds to the wheel hook. This is a high frequency vibration of the wheel truck assembly, which is essential to analyze foreground road holding and braking efficiency. So we move on to mode shape and relative motion. In mode 1, in phase, both the fuselage and wheel assembly move in the exact same direction together. The entire landing gear acts as a single lump unit. In mode 2, out of phase, they move in completely opposite directions. This represents high frequency wheel hook where the shock absorber works hardest to protect the upper plane body. And last but not least, simulation result. Our time domain numerical simulation directly validates our design principles. When a harmonic forcing function is applied from the runway profile, the wheel assembly takes the brunt of the high frequency displacement. Meanwhile, the fuselage displacement remains small and stable. This proves that our underdamped 2 degree of freedom suspensions effectively isolates high frequency impacts, ensuring a smooth ride and structural safety. Finally, extension to multi-degree of freedom system. First, higher resonance risk. More moving parts mean more natural frequencies, creating extra resonant points. The math becomes too heavy to solve by hand, so we must use powerful software tools like the block Lenzos solver to find them. Second, severe model interaction. Our basic 2 degree of freedom model only looks at up and down motion. In real life, vertical bouncing mixes with side to side and front to back movements. This causes dangerous instabilities like gear walk, where the landing gear bends structurally, and shimmy, which is violent wheel wobbling. That's all from us. Thank you.